Swayam Prabha. Digital India. Educated India.
Hello everyone. In the previous class, we discussed about Moore Coulomb failure criterion and Coulomb Navier failure criterion. I told you about the derivation of these criteria. Today we will take up the empirical failure criteria. I have been telling you that in case of the rock mechanics, many a times we have to rely on the test results and then we try to fit some kind of relationship between the two quantities which we get from the experimental data. So, when we get such type of any equation or any kind of fitted curve, fitted mathematical model, that is what we call as empirical correlation. So, today we will discuss few aspects related to empirical failure criterion. Before I tell you about these empirical failure criteria which are applicable in case of rocks and rock masses, we will learn some basics of the regression analysis, because most of the time you have some data on y and you have the data on x axis. You just plot it in Excel and then you try to see that which curve is the best fit curve between that data. What happens behind that? How Excel gives you the best fit data, whether it is a straight line or a polynomial of 2 degree, 3 degree or whatever it is. So, today we will first discuss about the basics of the regression analysis and then we will learn about some of the failure criteria, and finally I will be introducing you to the most commonly adopted empirical failure criteria for rocks, which is Hook and Brown criterion. So, to start with the criterion, as I mentioned, it is to be obtained from the experimental data. This data is plotted and then the regression analysis is carried out in order to establish the criterion. Question in front of us is, what is this regression analysis? Let us try to have a look with the help of a simple example of fitting a straight line between y and x with the help of some experimental data. So, please see here that I have here on x axis and here this is on y axis. So, we had some data, say that is say these are some data points which we already have. Now, we want to fit a straight line to this data, that means this kind of situation where it will have some intercept and it will have some slope. I really do not know what are these. So, let us try to see mathematically that how can we fit a straight line into the data set. So, let us say that the fitting of the straight line and this equation is y equal to a plus bx. This y and x, they can be anything. Right now I am just telling you the basics of the regression analysis. Then I will show you that how this analysis can be applicable in case of the rocks and rock masses. So say I represent here yi cap. These are the experimental values, and I represent another term yi for the modeled values. What does that mean? That this is what that we are getting from the experiments that I am going to conduct in the lab, and since I want to fit this straight line which has y equal to a plus bx, so this is the model that I want to fit into this experimental data. So whatever is the value of y that I will get from this expression, they will fall under this category, which are the modeled values. Now another quantity that I want to define is n, which is, say we have number of data points. Can be anything, 10, 20, 30, anything. It can be anything, the number of the experimental values is, this is what that we are going to get. Now when can I say that this model will be perfectly fitting this experimental values? When the error between this experimental value and the model value will be minimum. So I define another term z, that is the error between experimental and the modeled value, which is defined as z is equal to summation I equal to 1 to n, because n are the number of data points, and this is going to be yi cap minus yi whole square. This means what? That here we have the experimental value, here we have the modeled value, and the difference between the two, and take the square of that, so that we are not bothered about the relative sign of this difference. Either of the two can be larger or smaller than the other one. Now just substitute this modeled value. What we are going to get is I equal to 1 to n yi cap minus a plus b xi this whole square. This is what that we are going to get. Now in order to minimize this error, our objective is to minimize this z. A and b, these are the parameters of this model, and in this case it is the straight line. So in order to minimize this, from the simple mathematics, you know that we have to take the differentiation of this z with respect to a and b and make them equal to 0, and that way we will be able to determine the parameters of this model, which are a and b. To minimize this error, which is z, with respect to a and b, what is that? We need to do is del z del a equal to 0 and del z del b should be equal to 0. Now differentiate it with respect to, so what was the expression for z? First let us write that for our ready reference here, I equal to 1 to n yi cap minus a minus bxi whole square. This was our z. Now just differentiate it with respect to a. So what we are going to get is dz dA is going to be equal to C2 summation I equal to 1 to n yi cap minus a minus bxi, and for this minus a I will be getting one negative term, and then we need to make it equal to 0. So what I am going to get from here is summation I equal to 1 to n yi cap minus a minus bxi, this is going to be equal to 0. So you just split this up further. What you are going to get is summation I equal to 1 to n yi cap minus, see this a is not going to vary with respect to I. So I can take that outside this summation sign. So this is going to be a, but then it will be summed up over n times. So its summation is going to be n. Then similarly you will have b summation I equal to 1 to n xi, which is equal to 0. So from here I can obtain the expression for a in this manner, summation yi cap upon n, where this I is varying from 1 to n, minus b times summation I is varying from 1 to n xi divided by n. Make this equation number 1. Now we differentiate z with respect to b. So what we are going to get is this expression, that is 2 summation I equal to 1 to n yi cap minus a minus bxi, and corresponding to this term I will have minus xi, and since I want to minimize z, so I will make this equal to 0, and this is going to give me further summation xi yi cap minus axi minus b xi square, this whole bracket, which is equal to 0, and I is varying from 1 to n. Now the next step is going to be you further simplify this expression. So I write it summation I equal to 1 to n xi yi cap minus a summation I equal to 1 to n xi minus b summation I is equal to 1 to n xi square, this is equal to 0. Now we know the expression for this a, we just obtained. So I would like to substitute it here before we go for the further simplification. So take a look, this is going to be I equal to 1 to n xi yi cap minus, I have this bracket, then I is equal to 1 to n yi cap divided by n minus b times summation I equal to 1 to n xi divided by n. This was the expression for a. So I just substitute it like that here, and then this is summation xi, again the limits for I, minus b I equal to 1 to n xi square, that is going to be equal to 0. Now further simplify it, summation xi yi cap minus summation yi cap summation xi divided by n, and from with all the summations you will have the limit, which is I equal to 1 to n. So this is again I equal to 1 to n, here also I equal to 1 to n, plus you have b and the bracket summation I equal to 1 to n xi whole square divided by n minus summation I equal to 1 to n xi square equal to 0. So from here one can obtain the expression for b as summation xi yi cap minus summation xi into summation yi cap divided by n, and this whole thing divided by summation xi square minus this whole square divided by n. So this is how we can obtain the expression for b, and for a we have already obtained. So now we know a and b, they are known to us. Once it is known, I would like to see that what exactly is the accuracy of that. So for that I would define an index, that is r square, which is 1 minus summation of I equal to 1 to n yi cap minus yi whole square divided by summation of I equal to 1 to n yi cap minus y bar whole square. Now what is this y bar? So this y bar is the mean of the experimental values, which you can just obtain by summing and dividing it by the number of data points. So now what will happen if this quantity is small? See, if the numerator of this term is small, then what will happen? This r square is going to be larger. Smaller of the difference signifies that it is the better representation of the data by the model. Therefore, we can say that larger values of r square, what does that mean? That it will be close to 1. This is what is desirable. Because ultimately we want this numerator to be minimum, and accordingly we have defined this r square. Now there are many empirical criteria which are applicable in case of the rocks and rock masses. Once we have learnt about the basic of the regression analysis, we can go ahead with empirical correlations or empirical failure criteria that are applicable in case of rocks and rock masses. I took a very simple example and tried to show you that what do we mean by the regression analysis with the help of a straight line. Most of the time the model that is being fitted into x and y, it may not be a straight line. How to handle such type of the model? Let us try to have a look. So, the first one in this series which I am going to discuss with you is the criteria which was given by Murrell in 1965, and he suggested that sigma 1 is equal to sigma c plus b sigma 3 to the power a. So, you see here the data which you have may be the result of the triaxial data where you have sigma 3 and sigma 1 with you, and now sigma c is given as the UCS of the intact rock. That means that sigma c is going to be an input parameter which is already known to me. So, this is available to me. So, what are unknown parameters? These are A and B, which are the parameters for the criterion. So, I need to obtain this. The question is, earlier it was very simple, y equal to A plus bx, and we could fit very nicely in a simplified manner that data into this straight line. Now, how to tackle this? This is not a straight line equation. So, we have to do some kind of mathematical jugglery. See how. I can write this equation as sigma 1 minus sigma c, and that is going to give me b sigma 3 to the power a. Now, you take the log of this equation, that is on both the side of the equation, you take the log and see what you will get. Log of sigma 1 minus sigma c, and that is going to be equal to log of b plus a log of sigma 3. Right? Now, just imagine that this quantity is y and this quantity is x. So, what I will get from here? That is going to be y equal to log b plus ax. If I just compare it with the straight line equation just that we discussed, that was y equal to a plus bx. So, if we try to plot the experimental data in this space, that is on x axis I plot log of sigma 3 and on y axis I plot log of sigma 1 minus sigma c. And if I fit, say these are the points that we have, and if I try to fit a straight line to this, what this intercept is going to give me is log of b, and its slope will be giving me this parameter a. So, you see that this is how, by converting this nonlinear equation into a straight line in this fashion, we could get the parameters a and b. Once I know these parameters, I can just substitute it here and we can get that for this data, this is the failure criterion. Again, here you can just convert it, like let us say that you take this to be as small a and this you can take as small b, and whatever are these steps that we followed earlier in order to fit a straight line, you follow the same steps for the regression analysis and get a and b, or you can do that graphically in this particular fashion. Let us move to the next empirical criteria, which was given by Biniawski in 1974, and this was given as sigma 1 upon sigma c, that is equal to 1 plus b into sigma 3 upon sigma c to the power alpha. Again here sigma c is the UCS of intact rock which is available to us. We can just give it as an input parameter, and here alpha and b, these are the parameters of criterion. So again this is a non-linear equation. What to do with this? So again we will have some kind of mathematical jugglery. Take a look how. That is sigma 1 upon sigma c minus 1. This is equal to b sigma 3 upon sigma c to the power alpha. Again take log. So you are going to get log of sigma 1 upon sigma c minus 1. That's going to be equal to log of b plus alpha log of sigma 3 upon sigma c. So now if I try to plot the experimental data in this space, that is on x axis we have log of sigma 3 upon sigma c, and on y axis we have log of sigma 1 upon sigma c minus 1, and say these are the some of the data points. You just try to fit a curve to this, whatever is this intercept, that will give me the log b, and slope of this straight line is going to give me alpha. So once I know this b and alpha for the best fit line for this expression, this is going to give me the parameters for the criterion. Substitute it here and you will get the empirical criteria. Likewise, we have many empirical criteria. Let us take a look at them one by one. So the first one is the Balmer in this series, and it was given as sigma 1 equal to sigma 3 1 plus sigma 3 upon sigma t to the power b. So you see that this criteria makes use of the tensile strength, that is sigma t. Again sigma 1, sigma 3, they are major and minor principal stresses, and in this case b is the parameter for this criterion. Next one is given by Mogi in 1964, and this is defined by the equation sigma 1 equal to a plus b c to the power sigma 3. So here in this case a, b and c, these are the parameters for criterion. So in this case whenever you define the error, so in this case you will get z del A and del Z del B and del Z del C. All these three you have to equate to 0. So, you will have three equations and there are these three unknowns. So, you will be able to obtain these three parameters A, B and C. Similarly, another one was given by Hobbes, that was given by this equation sigma 1 minus sigma 3, that is equal to sigma C plus A sigma 3 to the power B, where this sigma C is again the UCS of intact material or intact rock. A and B, these are the parameters for criterion, and we need to again do the mathematical jugglery in order to carry out the regression analysis, and then we will be able to obtain these parameters A and B in such a manner that the difference between experimental value and the modeled value is minimum for that data set. This error may be minimum, but based upon the value of R square only, you need to decide whether this equation is fitting that data or not. It may happen that for a set of data, none of these equations may fit well. R square may come out to be very low. So, in that case, you have to search for such a mathematical model which fits the data in the best possible manner. That means for which you get maximum R square. The next empirical criteria in this category is the Hoeken-Brown criterion, which was given in 1980, and this is the criteria which is most commonly adopted in order to represent the failure criteria for rocks and rock masses. So, in the next class we are going to take up this criterion in detail, its equation, derivation, how to determine its parameter. So, today we discussed about the basics of the regression analysis, and with the help of a simple example of a straight line, I told you how to go ahead for the regression analysis and how to minimize the error between experimental value and the modeled value. Then, with the help of some of these empirical criteria, I gave you the idea that how the regression analysis can be applicable in order to get the empirical criteria for the rocks and rock masses. So, the next one, which is commonly adopted in case of these materials, rocks and rock masses, we will discuss in the next class. Thank you very much.